Hey guys, welcome to 9.2 notes, and today we're going to be talking about area between. So when I say area between, you're going to see that we're going to talk about area between two curves or two functions. So right here at the top it just says, while integrals can be used to find the area under a curve, they can also be used to find the area between curves. So consider the example below. Suppose you are a building contractor and need to know how much concrete to order so you can create a pathway that is 1/3 foot deep. The sidewalk borders can be modeled by f of x equals sine 0.5x plus 3, and g of x is going to be sine 0.5x from negative 2 pi to 2 pi. So the question is, how do we find the area of the top surface of the sidewalk? And then we're actually going to find out how much concrete we're going to need. So that means we need to find the area, the space between these two curves. So first we need to make sure we understand which function is which. So f of x here, this function right here, that's this top function here, f of x. And then our g of x function is this function down here on the bottom. Okay, I know that because this one has been shifted up 3 with the plus 3, so I know it's the sine function shifted up 3. So it should be going through 0, 3 right there. Okay, when we're looking at this problem here, we need to find two different things. So if we actually find the area from this function to the x-axis, which is what we have been doing, the area under one curve, what we would really get is just, I'll draw a little picture so you guys can see it a little bit easier. So we've got this, and it goes through here and then back like this. So we're actually getting all of this area. Unfortunately, that has area in it that we don't want, and it's got area that's missing. So if we take the other function, which is our g of x, our lower one, it looks like this. And if we find the area on this one, we're going to get those two pieces. So together, if we put those together, it's going to give us this extra piece here that we're missing, and it's going to account for this piece here, which we really don't want. So we can actually subtract that out. So what we're going to see is that we're going to need the integral from a to b of our top function minus our bottom function. And we're going to see throughout this that this is the common pattern that we're going to be looking at when we're talking about the area between two curves. So we're going to do the integral of the top function minus the bottom function, and this is all going to be with respect to our variable, which is usually x. Okay, so making sure we know what our top function is, so we already identified that, that's f of x. So we've got the integral, we know that our lower limit is going to be 2 pi and our upper limit's negative 2 pi, and our upper limit is going to be 2 pi. Then we're going to take the f of x function, subtract the g of x function, and we're going to take that with respect to x. Okay. What's nice about this is we can just take these functions and plug them in and then let our calculator help us do the math. So if I write this in my calculator, we just want to make sure that we're really careful and we know what we're writing. Okay. We've got the function, so this whole thing, the first function, which is sine 0.5x plus 3, and then we're going to subtract our other function, which our g of x function, which is sine 0.5x, and we're going to take that with respect to x. So I'm going to type this in just so everybody gets a reminder of what this is going to look like. Okay, I know you're not going to be able to see this the best on my calculator, but we'll make do. So remember, we hit math, and then the 9th option down there, you'll see the FNINT, so that's our function, and we're going to take the integral of it. So I'm choosing 9 and we're going to go from negative 2 pi to 2 pi. Okay, now in here, just be careful. I'm going to put this function inside a new set of parentheses, so sine of 0.5x plus 3, close that set of parentheses. Then I'm going to subtract my other function, which we just said was sine 0.5x. Okay, 2 closes of parentheses on that one right there, so we make sure we close that inside parenthesis, then that outside parenthesis. Then we're going to go and put with respect to x, and here we're going to get 37.699. Okay, so this right here that we're getting when we use Math 9 for this, okay, we are getting that the surface area is going to be 37.699, and remember our units here, it said that we were talking about feet, so this is going to be feet squared. Okay, now we're not quite done with the problem. That is this first part, the area of the top surface, so that's why it's the surface area. But now what we want to find down here is how much concrete do we need for the sidewalk. So to find the how much concrete, remember this is going to be a volume. Okay, so the volume is going to be our depth times our surface area. Okay, well, and that makes this pretty easy because we know what the depth is supposed to be. Back in the original problem it says the pathway needs to be 1/3 of a foot deep. And if this is already in feet, so I can just say it needs to be 1/3 of a foot and multiply by the surface area, which we said was 37.699. That is going to give us, when we type that into our calculator, 12.566 cubic feet of concrete. So this is really helpful for someone who's going to need concrete because they don't want to bring too much and they don't want to bring too little, so it's not wasteful. Okay, so we're going to work more of these problems. I'm going to show you a few shortcuts, so let's just talk about what that rule is. So down here at the bottom it kind of recaps this rule. So the area between two curves, consider the following graphs of y equals f of x and y equals g of x. They are continuous on the interval from 2 to 4. Okay, so if we want to find the area, this space between these two curves from 2 to 4, so notice how that's going from these intersections, we can take the area of the region under our f of x function, because that was our top function. Okay, it shows us here that this one's f of x, so this is our top. Okay, we're always looking top and then bottom. Then we see this function down here is the bottom function. Okay, so the integral from 2 to 4 of f of x minus g of x, so this is the top function minus the bottom function, will give us the area between those two. So it kind of makes sense. If I take the area of everything under the top, this part, that's too much. So then we need to get rid of all this stuff underneath the bottom curve that we don't need to only get what's left in the middle. Okay, so hopefully that part makes sense. Let's go to the back of that page. Okay, this part right here is just writing it out for you. The area of a region between two curves. If f and g are continuous, so that's important that they are continuous on the closed interval from a to b, and g of x is less than or equal to f of x for all x's in that interval from a to b, then the area of the region bounded by the graph of f and g are the vertical lines x equals a and x equals b. So that's just telling us where our upper and lower limit are. So if it's not given, sometimes we might have to find where they intersect and find that space. Most of the time, well, sometimes we're told what those are and sometimes we're not. Okay, so we're going to work through probably one more on this video, and then there'll be a new video for the other ones. So let's look here at example 1. Example 1 says, find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x, x equals 0, and x equals 1. So first, we just want to make sure that we see what interval we're actually looking at here. So let's take a moment and we're going to graph all of these pieces. Okay, let's start with the easy parts. X equals 0 and x equals 1. Okay, so x equals 0 would be this line right here, where every x is 0. X equals 1 is going to be this line right here. So that means we're kind of giving our left and right bounds, so we should know that we're going to be talking about the interval from 0 to 1. So we know this is going to be our A, and that's going to be our B. Okay. Then the other two here, our actual functions, are going to give us our top and our bottom piece. So let's just do y equals x squared plus 2. So this is the normal quadratic function shifted up 2. So that means instead of at 0, 0, it's going to go through 0, 2. Okay, and instead of at 1, 1, it's going to be up here at 1, 3. So I'm really only concerned with this piece of the graph. Okay, if I graphed the other parts, it would go over here like this, and I would get a quadratic function that looks, yeah, be helpful if I did a good curve here, like this. So we're really only concerned with this piece right here. Okay, even though it's going to keep going on both sides. Then the next piece is y equals negative x. So hopefully we're all confident that we know that this is a linear function that has a negative slope and is going to go through 0, 0, just like that. So if I sketch myself this graph, it would look like this. Okay, the piece that I'm really concerned with is this piece right here, because now I see all 4 sides to this piece that we want to find the area of. So we want the area of all this. So now we can clearly say that we know the top function and the bottom function. So this right here is our top function. This one down here is our bottom function. Okay, so we're going to take the integral from 0 to 1 of our top function, which remember, that one was x squared plus 2. And we're going to subtract out the bottom function, which was negative x, and we're going to take that with respect to x. Okay, when we punch this into the calculator, okay, again, on these, I am happy if you just punch them in. You do not have to go through all of the steps that we did in the previous chapters or the previous units. Go ahead and punch that in using Math 9, and we are going to get 2.83. Okay, so that is going to be the area, because it's going to give us the area of all this piece, and then it's going to give us the area of this piece. Okay, the reason we're actually subtracting, because this area down here is going to give us a negative, so when we minus a negative area, it's going to turn that positive, so it's really adding those two pieces together, but our equation is always subtracting. Okay, all right, I'm going to pause right here. In my next video, I'll pick up with example number 2.